Yeah. Is it okay right now? Okay, yeah, it's good. Uh, Last time I just trained using, I just trained a model that predicts in each frame whether the frame is actually a crash situation or not. And the model did around 0.70 accuracy, but there are other metrics that is very important. I guess we have them here. Yeah, yeah. Yeah, here you can see the F1 score of the non-crash non-crash with 0.46 and 0.80, and we should understand how does the recall of crash situations are 0.95. So 5% of the time it doesn't actually predicts whether the whether the frame is positive or I mean if the frame is crash or non-crash. But this is a very naive model because it takes only one single frame of information to understand this is a crash or non-crash situation. But crash is not detected by if we as a person we don't actually detect crash based on just one frame. This is a crash situation. No, we understand the previous frames and the previous frames and where the car is in the previous frames and understand how does the car moves across the frames and understand uh, based on this information only we determine whether the situation is a crash or no crash situation. Maybe the car is very near but the car is slow and it's not a crash. It doesn't actually get into a crash and doesn't predict to a crash as well. But there are cases where where frames shows that the car is near, and there could be cases where the car has a very high speed and very low speed. If the low speed is happening, the car could actually brake, and the target vehicle can actually brake and stop the crash. And in a high speed case, there might be no it should be our system should be alerted, should give alert based on the situation, um, based on its speed as well. But this speed information is not directly available. I just mentioned it in one of the videos before. The speed is not always available for us. So we have to use only the image information. This is a computer vision task. Maybe in future we will actually incorporate the tabular values in this one. But right now we are not going to do that. So the thing is that we need to understand how does the frames vary from each other. We can maybe do optical flow kind of analysis. How does the frames changes, the amount of changes happens that could actually lead to very very high prediction for crash situation, or maybe not all this situation. But this is not a very um amazing model. We have to incorporate uh, these frames as well. I mean, the previous frames before that as well, isn't it? Yeah. So for that, I just prepared a simple kind of model here. Okay, simple, just a small modification to the network, and I just increase the network size as well. We can do it in a small data set as well, but right now we're going to do it for just few samples. Okay, and this is the data set. So the data set, the torch data set looks like this. As usual, we have the data, and we have the video values, video IDs, and the targets already extracted from the data frame we have. And this time it's not frame by frame prediction, it's going to be video by video prediction. So we need to know how much videos we have, uh, how many videos, unique videos that we have. My god. Oh my god. ഇതാ നമുക്ക് തുറന്നോക്കാം. ഇവിടെ കത്രിക കത്തി ഒരു ഒന്നും നിന്റെ ഇല്ല. അങ്ങനെ അല്ലല്ല, അത് വേറെ കാര്യം ഉണ്ടായിരുന്നു. അമീക്കളുടെ മീറ്റിംഗ് ഉണ്ടായിരുന്നു 1 മണിക്ക്. 1:30 ഞാൻ അറിഞ്ഞത്. അല്ല, പോസ്റ്റ്പോൺ ചെയ്തു. അതെ, അവിടെ താഴത്തെ ഇവിടെ കണ്ടത്. അപ്പൊ ഇത് നോക്കിയപ്പോ ഇത് വന്നിട്ടുണ്ടാവും, അങ്ങനെ പോയതാ. തുറക്കന്നെ, നിന്റെ ആ കത്തി ഇല്ലടാ. ഇമ്മാരി മാടിയൊക്കെ പിടിച്ചെന്ത് ചെയ്യാ? എന്റെ കൂടെ ഇരിക്കുന്നത് ഞാൻ പൊളിച്ചൂടെ, ഇതിലൊക്കെ എന്തിരിക്കണ. ഇത് വൈറ്റ് ബോർഡ് ഷീറ്റ്. വൈറ്റ് ബോർഡ് സാധാരണ കട്ട് ചെയ്യല്ലേ ഉണ്ടാവില്ല, ഇത് ഷീറ്റാണ്. ഇതിൽ എഴുതാ. ടേബിളിൽ വെച്ച് എഴുതാനുള്ള പരിപാടിയാ. ടേബിളിലോ സ്റ്റിക്കറായി. വേണോ? ഫുഡൊക്കെ കഴിക്കുന്ന നിർബന്ധമാണോ? I just don't know why, but I had to go. Just I came back right away. Or whatever. Yeah. So this is what is happening here. We need to load the videos. This time we are going to do video by video, and we're going to predict how does it perform on each video. And based on each video frames, it has to predict whether this video is a crash or non-crash. This is still very simple and need a lot of modification, but right now it doesn't matter. Okay, it doesn't matter. We're going to start and do it like in this manner. So here's how it does it load the videos. We collect the images, we take the path of each video, and we have saved it using this format. And this is the format we saved it: the video ID and the frame ID. And the frame starts from 0 to 20, and 20 doesn't include, so it's 0 to 90. That's 20 unique values out there. So we just get every single value, we read it, we resize it to 224, and we do this. We add to the video tensor, and the video tensor is as you can see that it's a 224 comma 224 comma 20 channels, 20 grayscale channels. So it's like each frame is grayscale, and each scale is a frame is okay. Each frame gets a channel in the image, and we load this video tensor, and we get the the toaster tensor, the target values as well. And we this is for trained data set, so we just load the trained data set. And this time we changed the model. We're using Resonate 18. We can get this model from here, the Torch Vision library. The Torch Vision library, we had Resonate 18, which is very small model, so that's why I just started with this one. And I need the pre-trained weights of it. Resonate 18 has been trained on ImageNet dataset. It's a very big dataset, has like a lot of labels, and this weights is a very good starting point to start with. So we don't have to train the entire model. It could be like a lot of weight, a lot of values to be trained from scratch or from random values. So it's going to be a very headache for the optimizer to do that. It can do it, but it's going to take a lot of compute. And since this model was trained on um, color images, which has three channels. But our model is accepting grayscale images of 20 frames, and so that we have 20 channels. So the first layer of the backbone is called convolution one, and we just modify that layer using this method, using we don't modify, we just replace the first layer with the uh, our given layer. And you can see that we need 20 channels, and it should give us 64. Why does 64? Because the next layer of the resonate 18 accepts 64 feature maps. So we need to match with the model's architecture. So only then we can use the weights, and only then it's the using resonating and pre-trained model. If you want to use the pre-trained model, all, only if we match the shape of the data set, shape of the model we are choosing, transfer learning from, then only we can utilize the weights of that model and make this model predict, make this model optimize faster. Then only we can make this model optimize faster. Also, we have to change the final layer. The final layer should be um it should have only one single label, because our label is just 0 or 1, so just need one, and we need the probability between 0 and 1, and the probabilities maybe like some kind of threshold, maybe you consider like 0.5. It's a crash, it to crash. Less than 0 should be non crash, something like that, you understand, right? Actually, this backbone was trained on like thousand labels or 100,000 labels, but 100,000 labels. So we just needed to modify the file layer, and also we have to modify the first convolution layer as well. And we had to forward through the cellular backbone. So we just get those things. This is a classification engine. Classification engine is just an engine that actually takes the data set, takes the model, and creates data loaders, creates optimizers, criterion could be the loss function, and it does the training function. So it does do the training function for a lot of epochs. For each epoch, um, we do the training loop, and if there is a valid data set, we do the valid loop as well. And each step of the loop, of any kind of loop, I mean, whether it is a validation loop or train loop, we have to forward our inputs. We have to take our 20 channel image into the model and get the output, right? So that's what this is doing. It takes the input, it changes the images to the format. I will explain why we're doing this thing exactly, and we get the logic from here. We give these images to the model, and we get the predictions back. And if there is a label, we compute the loss, and we return the loss. If we don't have the loss, if we don't have the labels, we cannot compute the loss, so we need to give the predictions back. So this is part of prediction loop. So we just don't bother about right now why this function is doing. I used to do something like this every single time, so I really know how does it work. So when we get the loss function back, we have to get the gradients of each weight based on the loss. Okay, with gradient of loss with respect to each weight, and we need to we need to deposit some kind of gradient on each weight, which shows that which gives us the idea, which gives the model the idea that this is the amount of gradient that contribute to the loss. So okay, uh here's how would I put this thing. Each layer, each values has an influence to the target variable, right? I mean, if the prediction is banana, there are certain features that actually really contribute. Okay, let's take an example. We are predicting apple or banana. Okay, there are certain features that is very common for apple and very common for banana. Okay, suppose you just shown image to the model about apple. I predicted banana. The model has done something very stupid. To cause that stupidity, there are something inside the model that contribute to that stupidity. It's just not the entire model that contribute. It's not the entire. It could not be the entire model that contributed to the stupidity. There are certain points, certain neurons in the deep learning model that contributed very much to the stupidity. So when we calculate the stupidity, we need to know why, with respect to loss, how, with respect to the stupidity, how much this weight this neuron has contributed. Okay, how much this neuron has contributed to this stupidity, and we can and this loss dot backward just do something like uh, compute the stupidity out here, and the penultimate layer of the neural network, what is stupidity contributed by these layers and these layers as layers, and until the first layer of the model. So that's why it's going from backward. That's what we just doing loss backward. And when we do this thing, it will give each of these neurons the information that, yeah, you have this much information, this much stupidity you have done. You have done this much stupidity, and it's been just given information about how much stupidity it has done. And the self-dot optimizer, what it does is that it will take the stupidity, the gradients, we call this gradients, and we just change the values of that neurons based on this stupidity so that it could improve the performance. So it's based on learning rate, how much gradient should we learn each time. If you want to learn the entire gradient, maybe we have to do give like, the learning rate should be 1, but we don't do that because it's going to be very greedy situation, so we don't do that. And zero grad is that now there is gradients, so we have to clear those gradients, right? We don't want to influence the next prediction based on this one, so we just the gradient, we just avoid the gradients after that. Something like that. We don't want to do this thing in valid loop. Of course we don't have to do that. Yeah, so each epoch we will have, what is epoch number, we save the epoch number in this value, so we can do the symbol logging kind of things. That's the thing. And we do the train loop and the valid loop if we have the valid data loader. We don't have valid data loader right now, so this is what the engine do. It creates the, it's actually do take the model data sets and just train the model out of it. That's what an engine do, right? It takes the all the raw materials inside and just create the trained model out of it. And you can see this time, the reason why I using Kaggle this time is that my computer doesn't have a how do you say, doesn't have a GPU. It's using MPS, MacBook processing. I don't know what's for form of MPS. Full form of MPS. Oh, I don't know. Metal performance shaders. Yeah, I guess so. That's something like that. Metal performance shaders. Nothing, nothing what I say. But MPS has is not a lot. We don't have much RAM in it, and it's going to slow my computer. So I don't want to cruciate my computer on training models. If I have some other kind of information, some other um, place to actually train this thing on. So I'm using CUDA, and the CUDA, the GPU we're using is Tesla T4. We have two of them. You can see here the two of them. I just did a few experiments before here, so just it's just being um, occupied with something else. I just put um, empty the cache here. Sorry, it's CUDA. CUDA. So you can see that's getting cleared. Okay. Mm. So just do something like gc.collect as well. Oh, sorry. Just see again. Empty cache. We the garbage collected things, and we empty the cache. CUDA cache. So it will reduce the GP memory so far. Okay, that's good. It's not the best right now, but that's okay. You can at least see what is happening. And there is one more thing that is very important. As you can see here. Okay. Okay. So I just create a new image here. Create a new engine here, which will create a new model and the data loaders. And I would say what data loaders are. It's a generative generators. So what it do is that your data set, whatever you have here, your data set, it gives in it if you give in one index, it will give the video, it will give the 20 channel image and the target, right? I should be giving us the data in float, or it could be giving us the information in long, anything, any values, I don't care right now here. But this information is just a single video. But GPUs aren't very good for single process. I mean, just processing just single input. They are very good for batch processing. So we need to get multiple batches of information, and we should combine it to a single matrix, and we push it to the model and get the predictions for all the batches and compare it all the predictions to its corresponding labels and compute the loss. That's what GPUs are very good at. So data loaders, what it does is that it takes in the it takes in the information about how to use the data set, and what is the way of using this data set. And after understanding how do we use it, how do we use it, it you just do some kind of generation through the entire data set to create batches of information. It combines all the ah, it queries every single index of the data set until it fills the entire batch, and it combines them into a single batch, into a single matrix of torch. Get out. And so we can use it for other kind of tasks. So that's what data loaders are there. And it has workers as well. I mean, we can use multiple threads to do this kind of retrieving from the data set. So data set, this function not be data set should this function should it could be run in a parallel fashion. So two threads are working together to make this. What do we say? What do we say for this one? This function would be done. Two threads are working towards um, getting this video tensor and the target. So one should be doing for one index, other should be doing for the another index. So should it does the parallelism as well. So we don't have to care or we don't have to bother about all of these things. So we can do our training so fast. Okay. So this is what it does look like. We need to train a model. I don't know what happened, but no keyword argument. Okay. So what is it he said? I gotta understand it. I can understand it. Uint 8. I guess this will work. No issues for this one. I hope so. Yeah, I was good. But you can see, even though we are using GPU, what the hell is happening here? What the heck is happening here? And at last, byte tensor, the type was byte tensor, the weight was this type. Uh-huh. That shouldn't happen, but let's see. Where do we get this thing? Hmm. We're doing float here. Why the issue? Let's see how does the image, the type of images. Let's see what is the type of the images. Okay. Then only we can show you the information about. So what it's doing is that we are using a train batch size of 128. So the two workers, we have the two threads in this process. So we use two workers, each will do 64 index, and it will prompt this video crash that I said that each of them will prompt this video crash that I said about I need this index, I need this index. It will return this video index, video crash data set will return those things, and that will loader just combine them. Yeah, it actually worked. You see, I was right. I was right. Okay, so it will take the all this okay, each of these workers will say that I need this index, I need this index. At last, it will get all this required, it's required one, and after that, What it will do is that it will just stack it together and give it back and put it outside. So it's just a parallel uh, combining, or ag I cannot say aggregating. It's just doing some kind of so this was good, but this was 34 minutes. Even though we are doing this thing in CUDA, why does it take this much time? Even if we're doing this thing in CPU, just hard coding it here, so we can just understand how does it work in CPU. We we can understand how much in information do we get. Ah, sorry about it. Uh, I understand. I understand. Dot CPU. Dot device. Yeah, I sometimes I miss things. Yeah, it's works. You can see all the work is going to be for CPU itself. Of course, it's expected. I don't know how long it's going to be, but let's see how long it will be taking us to reach that. See, the involvement of CPU is getting higher here. It computed one batch, and why doesn't? Yeah, it's 1 hour 7 minutes. You might think that okay, CUDA has done. I mean, CUDA has done some kind of improvement. As it's now 1 hour. It's now 1 hour 23 minutes. But do you know how much did CUDA did? It was just 40 minutes. I don't think CUDA is just capable only for that. We have few issues in our network. Okay. One of the thing that we don't actually. Okay, sorry, something is not going right here. Yeah. So, okay, I just get this thing outside. Okay, here you're using QDA itself. Can understand what is the main issues. There are few things that I did to make this much faster. I would just explain those things, but still not faster yet. One of the thing is that here I loaded the images to a tensor and store it in a uint8 matrix. Images are unsigned integer 8 matrix. Okay, we can actually represent those in these from value 0 to 255. You can use 0 to 255 values to represent an image, where 0 represent white and 1 represent black. In case this is grayscale, it was represent like that. So we say those information in uint8. The reason why I did like that is because it just takes 8 bits. So it just takes just a small information to store in the memory, but not just the memory. I will show the other part of this one. Here we are taking this images. Images could be from the data set. I said data loader just combines it and batch it. That's all what data loaders do. and generate it for, epochs after epochs. That's also a job of data loader, to shuffle it and generate new samples, epochs after epochs. That's a certain kind of certain kind of things that it do. So yeah, here it takes the images and it sends this data to GPU. Okay, now is the real thing. If this thing was an uint8, or if it was like, float 32 values, we have to, you know 4x value should be transferred from CPU to GPU, and that's a very lot of information from CPU to GPU. And it's not very slow, but it's slow. We should actually improve the situation. That's why I didn't want to do float 32 at that moment. I didn't want to normalize it to 0 to 1, because neural networks need values from 0 to 1. Doesn't values like integers or something like that. Isn't trained, or is not very good at doing those computations so fast. So it's always better to better to scale our input into across 0 to 1. So if we have scaled it in the data set part, this information was scale this if we do this in the scale on the data set part, we will have to store them in float 32, and we would have to send for CPU send float 32 values from CPU to GPU, that is 4x more values, and we have to permute. Permute is just changing the structure of the input. By in PyTorch, the structure of the input looks like the convolution layer actually accepts in a format. We can see the nn.con2d layer here. It accepts yeah, it accepts information in this way: the number of batches and the channel information, and the rest of the information. It could be in our case it's yeah, this is the main information. Yeah, the number of batch, the channel information, channel inside channel. The channel should be the second dimension, and the next dimension should be the height, then the width. So that's the reason. Now we have seen that we have stored the channel information here at the third dimension. Well, so we just take this this channel dimension. This is the batch dimension. This is the channel dimension. This is the height, and this is the width. That's the way. Non-blocking is just don't have to. Um, we can compute other things without when we are doing this transfer from one device to another one. We don't want to slow down our process. That's also a small kind of improvement in the speed. This gives us all improvement in the speed. Also, the reason why I did normalization here is the next reason is GPU can do parallelly. If you're doing this thing in the CPU, it's going to do one by one, but CPU can just do this thing for the entire matrix at once. Yeah, that's amazing, right? We do the same for um labels. You can see that I did if you are doing float here, or if you're doing float here at sometimes we accidentally do. This is going to take the entire int int 8 int 8 8 bits into 32 bits, and then transfer, then do the permute. It's going to be taking a lot of time. We are just making so much simpler. We're doing the same thing but much simpler. So we shouldn't be doing this thing here, by the way. we should convert the float labels to the float, so we can only then only we can compute the criterion. We can, I think so. I don't remember. Uh, nn dot bce. We're using binary cross entropy with logit loss. So I don't know what does it take. I don't remember. Sometimes I don't remember at all. Mm, I don't know what kind of value does it takes. Maybe we can try the other way. You can just try it and let me know how does it do for the integer value itself. And this is what the this is the symbol modification that we have done so far. We just reduce the number of CPU to GPU conversions, and we do maximum parallel operations as possible. But still it doesn't isn't faster. You can see even we did all of these things, it wasn't faster, right? It was so slow. It was like 40 minutes or something. And that's the main issue of that's what I want to show in this one. Why does data transformation is so important? Since we are doing video by video, what we were doing is that each time the model is trained, it reads an image. You can see there is an image of all the frames of the video and combine them and then produce as input. So for each video, there is at least, like, 20 IO operations, and 20 IO operations is hell lot of a task, and that's a very good there is a very bottleneck out there. What I'm saying is that in order to compute one single index input, you have to do 20 IO operations. We are using 128 batch size. So 128 times 20, you have to do 250, 560 IO operations for a batch. Imagine that. IO operation is the worst kind of performance issue we had so far. So we have to improve those things. We don't want this to happen for every single frame. And after every epoch, we are going to do this. Not sure. I don't know. Not necessarily, because we are using pin memory, because once we have computer for one epoch, the next epoch we will have a cached input, and we can use those input, and the next epochs could be very faster. I never tried it because this itself is taking, like, 60 minutes. Yeah, you can see here. Last time we did uh last time we did some operations on on the last input. So it has already cached it. So that's why it's taking less time. This moment is taking less time for the first few epochs, for first few frames, and it's getting longer, right? You can see that it's getting longer and longer, because so far it has been using the cached one, and it's getting to know more about the uncached ones, so it has to compute it again. So why don't we do the caching by ourselves instead of doing it by the before computing, without doing uh, uh, not doing for every single step. We don't want to do it for every single step manually. Why don't we transform our data set from frames to a video matrix. I mean, why don't we store this for every single video and only access them, and we just access those metrics at once, one IO operation. We get those back, and we train our model. Do you understand? We store this 20 frames in a tensor in somewhere in a cache directory, and when we are training it, what we are doing is that we we ask the data loader, okay, load this index. So when it goes to the data loaders ask the data set that I need index 1. Okay, in the data set say, oh, already had the cache for this. I already had the cache for that. Okay, then give me that. I'll already have the cache, and you can take that. That would be amazing. Just one IO operation, and if there's 128 batch, just 128 IO operations. See, this reduces 20. This makes it 20x times faster. This process just makes it 20x faster. But there's an extra kind of process and extra kind of overhead. We need a more storage to save this thing, and we have to spend more time before training to make those caches beforehand. We can do something like that. What data loader does for first epoch, it does the training as well as the caching, and for the second epoch, it just uses these caches. We can do something kind of very intelligent way. For now, I'm just showing a simple cache kind of cache caching way. So I do mention a cache directory here. If we have mentioned a cache directory, we'll do the caching. We create a cache directory, and we build the caching. We have a single threaded cache, and we have the multi-threaded caching here. So what does it do? I will say that as before, we load the yeah, just a minute. Okay, we load the videos as usual. Every single frames here, and saving it to the images, and finally saving it to the. Why do we need images, by the way? Absolutely, I didn't think so. That was a very unfortunate variable there. We get all these images here. We get the path, we read it, resize it, store it in this numpy matrix. We convert it to torch in uint8 itself. We have seen that we cannot use this thing, and we return the video tensor. Okay, that's what it will do. So what we do is that we create a cache file for each of the videos. So with the video ID and video vid underscore video ID, we save it in this. If that path doesn't exist, we save it here. We load we that path doesn't exist. We create the we okay. We say the video ID, and if that video ID doesn't have a cache, it will get the video tensor for that, and save it. Okay, understand it? Yeah, yeah, yeah. And this is a single thread. You just take all the VIDs and save it, and returns true. But we don't want it to be single thread. It's going to be taking 40 minutes or something. We have to use every single threads we have. I think so we have 4 threads. total, and we do thread pool executor, and we save cache in through 4 threads, and it's going to be so much faster. So that's what we are doing here. And here's the get item function looks like. If the data loader asks for an index, it takes the video ID. And if there is a cache directory and there exists a cache for this file, this video, then load that cached matrix. If there is no cached file or cached directory, then you do the usual thing that what we have done in the last crash data set, and return them back and make the target to toast.long, and that's what happens. And you can see that we have to do one more thing. I just made a few cleaning here. I did a small. Okay, RF.